Hello everyone, Dr. Chen here. We're going to talk about how to solve a problem using Newton's first law. So first, we need to recall what is the definition of net force. Now remember, forces are vectors. So if you want to add up forces, you need to add them up as vectors. Now we have one object. So if we have force F1 and force F2 acting on it, we add them up, we find the vector sum, and we see this is F net, and we see F net is F1 plus F2 as vector. So it means the net force have the same effect. So if you only apply F net, it will have the same effect as if you have F1 and F2 at the same time. This is a definition of net force. So after that, we're ready to present Newton's first law. It says everything that will be in its state of being at rest or moving uniformly straight forward, so basically is constant velocity motion. At rest or constant velocity motion. Everything will stay at rest or moving uniformly at constant velocity motion unless, except insofar, you have there is a force compel it to change its state of motion. So to transform it into some easier to memorize statement, we see Newton's first law tells us. Newton's first law tells us that if net force is zero, acceleration is zero. So acceleration in zero summarizes the two statements. So an object at rest will stay at rest, so there's no acceleration. An object doing constant velocity motion will stay doing constant velocity motion, no acceleration, right? So Newton's first law can be summarized as no net force, no acceleration. Net force zero, acceleration zero. So this example we discussed. So you have two cars. They have very different mass and different velocity. McLaren is driving much faster. Then you have Beetles driving much slower, 5 km per hour. McLaren driving 150 km per hour. Okay, which car has greater net force? So you can pause it, think it for a few minutes, and then come back and we'll discuss what's the answer. Okay, we'll come back. So the answer is the net force on either car is the same. And why is that? Because both cars are doing constant velocity motion. And Newton's first law tells us A equals zero, net force is zero. This is Newton's first law. So the net force on both cars is zero. Another example. So you have an elevator. You have an elevator. It's been lifted up at a constant speed by a cable. Ignore air resistance. Ignore friction. Then we ask. So you see on the elevator you have two forces, right? Tension and weight. We ask which force is greater. Now you can think again for a few minutes, then come back. We'll discuss the answer. The answer should be B. It's also because Newton's first law. The elevator is moving up at a constant speed. So basically it's a constant velocity motion. Constant velocity motion. Gives us acceleration is 0, gives us net force is 0. So T in magnitude has to equal weight. So they are in opposite direction. That's why to add up to net force 0. Then some of us might still wondering, okay, how does the elevator going up if the net force is 0? Now, of course, if the elevator starts from rest on the first floor, then it intends to change its state from at rest to moving up. Then there has to be a net force greater than 0 and pointing up. So the elevator will have acceleration pointing up and start moving. This is if you want to change the state of motion of the elevator from at rest to moving up. Now you need a net force not 0. But as long as the elevator started moving, you only need to keep the net force to be 0, and the elevator is going to maintain that constant velocity motion, maintain that constant speed. Only requires net force 0, and it has to be net force 0 because of Newton's first law. You just kick a rock, and the rock is sliding across the ground. So at the instance the rock is sliding across the ground, what are the forces acting on the ball? Now, I'm pretty sure we have gravity from Earth and the rock, we have normal force from the ground and the rock, we have friction on the rock, right? But do we have the force of the cake? See, the person is here and the rock is here. Is there a cake force on the rock when the rock is not in touch with the cake anymore? The answer is no. Now the cake force only acts for a very short amount of time to change the state of motion of the rock. Now, as long as the rock started sliding on the floor, there's no cake. So the answer is A, B, D. Okay, now we are ready to present the strategy to solve equilibrium problem, basically using Newton's first law to solve a force problem. An object in equilibrium means is either at a rest or moving with constant velocity. Now also it has to be moving in an inertia frame. Now when an object is at rest or moving at a constant velocity, then we can make a statement that the net force on this object is 0. And if we do our analysis in 2 dimensions, net force equals 0 means net force in x is 0, net force in y is 0. Because if either of them is not 0, your net force is not 0. So they have to be at 0 at the same time. Net force equals 0 means net force in x direction is 0, net force in y direction is 0. So this is a step we need to follow to solve this problem. First, sketch the situation to help us understand, and then draw free body diagram for the object we're interested in, that is in equilibrium, and then find out what are the forces, what's the magnitude of the forces, how many are already given, and you have to be careful that we only include the forces that acting on the object in equilibrium. Only the forces acting on the object, not the forces that is object acting on other things. And then we set our coordinate system for a free body diagram. and then we solve, right? We find the component of each of the force, find the component in x, component in y, sum all the x components in, and it should equal to 0. Sum all the y component should be equal to 0, and then we solve the equation. So let's do it with two examples to demonstrate how we solve the problem. We have two ropes. We have two ropes joined here, and then we have the third rope hanging a weight. We know this angle is 60, this angle is 40. And first one, it has to draw free body diagram for the knot. So there should be three forces, right? Let me call this one T1, call this one T2, call this one T3. So those are all the three forces acting on the knob. It asks us to figure out for T1 and T2 which force is larger. Okay, we'll do that in the next screen. And then the second question, if the string can only sustain a 5,000 Newton force, what would be the maximum weight that we can hand here so the string doesn't break? So first, let's see, we already draw the free body diagram. This is T1, this is T2, let me build my X like this, and Y. Then I have T3. Okay. So I build my X, Y, Z like this. And if I have vector is angle is theta, I have AX is A cosine theta, AY is sine theta, right? A sine theta. I want to follow this formula to find out my components. But then I need to know what's the angle of each of my force. What's the angle of T1? So you always need to find out what's the angle of your vector from 0 degree. This is 0 degree, so your T1, our T1 actually is 120 degree. T2 is 40. T3 is 270 degree. So I have the x component have to add up to 0, right? The x component. So you have T1 cosine 120 degree, which actually now gives me a negative number. T2 cosine 40 plus T3 cosine 270. Of course, this is 0. Cosine 270 is 0. T3 doesn't have x component. Makes sense. And it can also, so now this equation also tells us T1 cosine 60 degree and cosine 40 degree is greater than cosine 60, so T1 is greater than T2. Then the next question, the maximum force on the string T1, T2 is 5,000, so it has to be T1 equals 5,000 Newton. Now T1 is T2 cosine 40 degree. divided by cosine 60 degrees, so you can calculate T2 from T1. And plugging all the numbers, we find is and this is from x direction. Now I found out what is T1, what is T2. Now we need to find out what is T3 if T1 is 5,000. So it has to be in the y direction. We build the equation, all the y components add up to 0. All the y components add up to 0. So first T1i, T1y, T1y, which is T1 sine 120 degree, T2y, T2 sine 40 degree, T3y, weight sine 270 degree. Add up to 0. So I have my weight. This gives me -1, so you can move this term to the right, give you T1 sine 120 degree plus T2 sine 40 degree. The plug in T1 is 5,000 Newton, T2 is 3,263.5 Newton. Calculate what is sine 120, sine 40, and we find the maximum weight we can handle, 6,400 Newton. And I would suggest to you to do this example, which is essentially the same setup as the example I just solved. So you have string 1, string 2 hanging a mass, and the angle is 30 degrees. We want to find out what are the forces F1, F2, and F3. Now, of course, F3 is going to be, and then what is F1 and F2? I will highly recommend you solve this program to prepare for exam 2. So let's do a problem that is related to the friction net we're going to do this semester. So you have a mass, you put it on a ramp, it's at rest at first, and we know the coefficient of static friction between the block and the ramp is 0.35. So we want to find out what's the maximum the ramp can have, and the block did not move yet. The maximum angle we have. And you can see the maximum angle tells us we have a maximal static friction. And we also know the maximal static friction we can have is mu s times n. So we need to solve what is n and what is fs. So, and also, if the block haven't moved yet, is at rest at the beginning, and it haven't moved yet, so net force has to be 0, right? And then we follow the procedure, draw free body diagram. What are the forces acting on the block? Of course, we have normal force, we have static friction, we have mg. Those are the 3 forces we have. If I build my x this way, my y this way, then I have also do the same thing. What are the angle for all the forces? The normal force is pointing in the positive y direction, 90 degree. Static friction, negative x direction, 180. A little bit more tricky is what's the direction of the gravity? The answer is the direction of gravity is 270 degree plus theta. Theta is angle of the rim. And I will show why the angle for gravity is 270 degree plus theta in the next slide. So first I want to prove this angle equals this angle. How did I do that? So I'm going to call this angle beta. So apparently you will see the angle between gravity and the negative y direction. Let's call it theta prime now, plus beta equals 90 degree, right? So beta plus theta prime, which is the angle between gravity and the negative y. And then we also have beta plus theta is 90 degree. This is theta, this is beta, is inside a rectangle. So beta plus theta has to be 90 degree. Beta plus this one also has to be 90 degree. So we have theta prime equals theta. So this angle, which is angle between negative y direction and mg, has to equal the angle of the rim. And now if you want to find out the angle of mg, you need to start from 0 degree, go counterclockwise, 90 degree, 180 degree, 270 degree, and then go theta move. So the angle of mg is 270 degree plus theta. And now, what's the x component of mg and what's the y component of mg? This is x component of mg is mg cosine 270 degree plus theta. And if you do trigonometry, you find that it's actually mg sine theta rather than cosine theta. Because mg cosine, this is angle of mg. And the theta is only just happen to be the angle of the ramp. It has nothing to do with the angle of mg at the first. But after some geometry, we find out the angle of mg is 270 degree plus theta. So x component of mg is mg cosine 270 degree plus theta. And trigonometry tells us is mg sine theta, and it's pointing in the positive x direction. Now the y component, mg sine 270 degree plus theta. If you do trigonometry, you find it's actually negative mg cosine theta, pointing in the negative y direction. So we find out the x component and the y component of mg now. Now we're ready to do our calculation. In the y direction, we have normal force equals 0. We have normal force, net force in y direction equals 0. Normal force plus y component of mg, which is negative mg cosine theta, we just discussed, add up to 0. We find the normal force is mg cosine theta. And then in the x direction, net force also has to be 0. So what are the forces in the x direction? You have the x component of mg, you have static friction, you have mg sine theta subtract fs equals 0. Then I also have fs is mu sn. This is my fs, right? And I also have my n is mg cosine theta. So which gives me an equation mg tan theta US G cosine theta equals 0. You can eliminate mg from both terms, and in the end we find the mu s equals sine theta divided by cosine theta equals tan theta. Now we're ready to find out what is theta, right? Theta is tangent inverse of mu s. So if your mu s is 0.35, your theta is 19.3.